Hi everybody, welcome back to Chem 121. Let me just pan the music out here. I mean, it's already doing that on its own, but... let's see here. So, we are going to be doing Chapter 4 today. We're going to do more of it. I'm going to try and do as much as we can, because I would like to have Chapter 4 done this week. That does mean it's very likely that I will have to use Wednesday, tomorrow, that is, for an extra lecture day, to finish up Chapter 4 so that we can get into Chapter 5, because it's on the exam next week. Some students have been using the Discord to ask questions. That is great. Please continue to do so. Remember that that's kind of your way to do office hours with me, is you go in the Discord and post questions in there and just like take pictures of your work or take a snapshot of the screen or whatever. I'm going to start with lecture, and then at the break, I'm going to talk a little bit about the lab, and then we'll continue after that, because lab number 2 will be assigned this week, and it will be due next week. Okay, so the only other thing I can think to say is that quiz number 2 is going to be due on Wednesday, which people have probably been working on. I didn't put the due date for quiz number 3 up there because it's sometime next week, so... check the calendar on Canvas for that. I believe it's due Monday. Okay, let's go ahead and get started here. So, the first thing I want to talk about is from yesterday's lecture when we talked about periods and groups. And I said sort of nebulously, I guess I could say, that they had something to do with how electrons worked, but it was sort of beyond the scope of this class, and that we weren't going to pay much attention to it in a high level of detail anyway. But we will talk about it at a very basic standpoint. And so what I'm going to do is I'm going to get p-table up here. So if you have your periodic table handy, go ahead and pull that up on the screen. Let's see here. Here's p-table, and we'll put this on the screen here. That's too big. Let me just resize it real quick. There we go. Oops. All right. It turns out that the periodic table is structured in this fashion for a very particular reason, and that reason is electronic structure. What that means, the word electronic, is how are the electrons arranged around the nucleus? Now, if you look at the little cartoons that I have here, these are models. They're not exactly what's going on. Electrons do not live on constrained rings because they repel each other. They push each other off of the rings, right? So electrons don't live like this, but they live in this sort of pattern where only this many can be this distance from the nucleus. And the reason for that is there's just not enough volume to have more than, say, 2 electrons around the nucleus when you're this close. And then you could go further out, but there's only really enough room for 8, and so on and so forth. And so when I go over to this picture, you can see that if I count across, okay, the first period, there's only 2 elements on it. And then the second period, there's only 8 elements on it. And then the third period, same thing, there's only 8 elements on it. And then the fourth period, there's actually a lot more, because there's more space that far out. You can hold more electrons. So the takeaway from the periodic table and how it's structured is that the period, going left to right, is what layer of electrons you are on. So the first layer is the closest to the nucleus. Then you have the second layer, and then the third layer, and so on. And the group number, if I go back to this again, the group number will tell you how many electrons are on the outside, sort of. You'll notice that there's an issue here because the groups go from 1 to 2 and then all the way to 13, 14, 15. We skip a number 10 here, right? So the ones digit tells us how many electrons are on the outside for these guys over here. Maya, please. I fed you. I made sure of it. No, don't come closer and bug me. Oh. I'm trying to lecture, and she's sitting there yowling. She's not normally this bad. So, when we go over this diagram, for helium, and I want to count how many electrons are on the outside, the outermost ring. These are called valence shell electrons, by the way. So those are the ones in red here that I'm highlighting with yellow. These electrons are represented by whatever group number the element is in. Now, helium is kind of an exception. We couldn't put helium in group 2 because it doesn't behave like a group 2 element. It behaves like a noble gas. So it lives in group 18, but because there's only 2 things in that row, it only has 2 electrons. Every other element follows this pattern, including hydrogen. Whatever group it is in is going to be the number of valence electrons, at least when you look at the ones place of that group. And I think that that's set on this next slide. Yeah, here we go. Now, if we're using the A notation for groups, then you just use the number that's shown there. So I personally like the A notation better. However, it's starting to disappear off of most periodic tables, and most periodic tables just are numbered 1 through 18. So remember that the number of valence electrons, that is the number of electrons that are on the outside, is... So this is the number of valence electrons. And that is the ones digit in the group number. So a group 15 element, such as nitrogen, would have 5 valence electrons. The number of valence electrons is going to be very important for us very shortly. Now, why do we care about just the valence electrons? Well, if I go back to this diagram, and I have another atom, I'm going to have my atom look like this. Here's my atom. I'm not circling helium because it's important, but I'm just drawing this here. And I'm going to bonk into chlorine. So I'm going to have an atom bonk into a chlorine atom. The electrons that would encounter my mystery atom that are flying by would be the ones on the outside. So all these guys out here, right? The ones in the middle don't really see anything at all because remember, electrons repel, yeah? And I have electrons on the outside of this atom too. So what's going to end up happening is that if I have any electrons that can interact with these other electrons, for example, fill in these gaps, for instance, because electrons won't repel if there's a gap, but they'll repel if there are electrons themselves. So I can have my atoms interact with each other, but only the outside electrons get to do the interaction. I guess an analogy that I could make would be like if you shake hands with somebody, your hands are what are touching and not, say, your heart or your lungs or your organs, right? Like your heart and your organs are never ever exposed to the outside. That would be really creepy and bad, right? Like the same thing happens with the core electrons. They're sort of just tucked in the middle and they never get to see the outside. Only the valence electrons do. So the valence electrons are the only part that we care about for bonding because they're the external ones. They're the ones that actually engage in it. All right. So what we're going to do is we are going to take those little, these things right here, these little models that we had, and we're going to represent these with symbols, and these are called Lewis symbols. And the Lewis symbol is possibly the easiest thing that we're going to do in this class, but also extremely important foundationally speaking. Like this is one of the most ingenious ways of representing bonding that I feel like if I had to describe like essential skills in chemistry, I would say the Lewis symbol and the Lewis structure, like so important. Despite how basic it is, because it helps us understand so many things. And it's going to be fundamental for us in Chapter 5 as well. So, to draw the Lewis symbol of any element is a 2-step process. The first step is to look up the symbol of the element on the periodic table. So we would again go over here and find the element that we are interested in. So if I wanted a Lewis symbol of, say, fluorine, I would have to start by writing an F, because that is the Lewis symbol. And then what I would do is I would draw dots around the element, 1 dot per valence electron. Now, there are some caveats to this. And those caveats revolve around the fact that electrons repel. And we'll see that in just a second. All right. We're going to draw the Lewis symbol for sodium. So the first thing that we need to do is draw the atomic symbol. Well, I've already written the atomic symbol for you in the problem statement right here, yeah? So, there you go. We'll just plop it on the paper. And then step 2, draw a dot for each valence electron. So if we go to the periodic table, sodium is in group 1. Here it is right here. So it would have 1 valence electron because the ones digit of the group number is 1. So I'm going to go back to my diagram here, and I'm going to draw 1 dot. Boom, there you go. That's the Lewis symbol for sodium. Two-step process. The hardest part is counting valence electrons and finding which group it is in on the periodic table. You just draw that many dots. Remember, we're only using the ones digit, so the highest you can go is 8. What about group 9 in the middle, Wes? We'll talk about that in a little bit. All right, let's do oxygen now. So first I'm going to find oxygen on the periodic table. So there it is right there. Oxygen is in group 16. Therefore, it must have 6 valence electrons. So we're going to plop the letter O down. I got to click over here to do that. So there's our O. Boink, there. And we're going to draw 6 dots around it. Now, I have 4 sides that I can draw electrons on, more or less, right? Top, bottom, left, and right. Now, if I am to draw all of my electrons huddled together, like, say, this, 1, 2, 3, 4, 5, 6, my electrons are going to push each other apart, right? And they will repel in such a way that I use up as much space as possible. So I have this empty spot here. There's not going to be an empty spot when I have my electrons jammed together. So the rule for drawing electrons is that you do 1 per side at a time. And then if you have any more electrons left over, then you pair them. So this would be the answer for O. I would draw 6 dots, 1 per side, because electrons repel each other. And then I fill in the extras so that I have 2 per side for the sides that need it. So here's an acceptable answer for oxygen. Now, interestingly, it does not matter which side you put your dots on. So this is also an acceptable answer, as would be this, where I have the pairs opposite from each other. That's totally okay too. So any orientation where I have 2 pairs and 2 unpaireds is fine. What would not be okay would be the first thing that I drew before, where I had the empty space here. This is not alright. Okay, so make sure that when you are putting down your dots, you are putting them down 1 at a time, per side on all 4 sides, and then pairing them only once you have to. Alright, and so that's what my slide says there. So what I want you to do, I'm going to give you like 2 or 3 minutes to do this, is I want you to take the periodic table from P-table, and I want you to draw the Lewis symbol for each of these elements. So for example, carbon, we'll go look up carbon on the table here, count how many valence electrons it has based on what group it's in, and then draw the symbol appropriately. Do that for all the elements shown. Okay. Now, you obviously cannot type this into the chat. There's no way to draw this picture in the chat. So what I want you to do is when you're finished, type like done or something like that, just to let me know. I'll give you 2 or 3 minutes, and then we'll go over the answers together in just a moment. So see you in a bit. All right, one more minute. We'll go over the answer. All right, let's go over the answer here. So, if I pull up the periodic table here, you could see that carbon is in group 14. The ones digit is a 4. So that must mean that carbon has 4 valence electrons. So what I would do is I would do this. So here's my carbon. I'd go 1, 2, 3, 4. There you go. All right. For lithium, if I go back to the periodic table and find lithium here, there it is. It's in group 1, and therefore should have 1 dot, and there it is, right? No, be careful with lithium. Lithium's kind of the only one that this happens with, where you're drawing valence electrons in. Make sure that you don't mistake the dot on the eye for a valence electron. You still have to draw its dot. So just be careful. All right, you can go back and to look at the periodic table now, so I'm not going to keep putting it on the screen, but sulfur is 6. So we'll do this. 1, 2, 3, 4, 5, 6. Again, you could put those paireds and unpaireds on any side, as long as you have 2 paireds and 2 unpaireds. Chlorine would have 7 valence electrons, because it's in group 17. So it'd look like that. Aluminum's in group 13, which is 3 valence electrons. And xenon in group 18 has 8 valence electrons. And there you go, you're all set. All right, you can draw a Lewis structure. Hooray! We're going to make things a little more complicated throughout the next few chapters, but this is the foundation. We're going to start here. All right. And there's the homework practice for that section. So, let me know if you have any questions. All right. You probably noticed that there is no group for any of the elements that I selected that goes beyond 8. In fact, if you had to draw more than 8 valence electrons, where would you put the 9th one? You'd have to put 3 to a side or something like that. It turns out you can't do that. And there's a specific reason for this. And that's where this octet rule comes in. The goal of elements is to try and attain 8 valence electrons. And, excuse me, this is just the pattern that we observe consistently, is that elements want to get 8 electrons. If they manage to do so, then they become much more stable. They become much more inert. They don't react as much. For instance, the noble gases. All the noble gases are in column 18. And since they're in column 18, they must have 8 valence electrons, except for helium, which only has 2. Helium is the exception in that group. But all the rest of them have 8 valence electrons. And what do they do in terms of chemistry? It turns out that they do absolutely nothing. Neon does not react with anything known to human civilization. I think there might be 1 or 2 argon complexes, and there's very few krypton and xenon ones. As a general rule, they don't do chemistry. You can breathe them, and the only thing that will happen is that you'll eventually suffocate because you aren't getting oxygen. But they don't hurt you. If you inhale argon and then exhale it and then breathe back in normal oxygen, you're fine. In fact, you may have heard this experiment done by, like, random science teachers where they have a balloon of helium and then they inhale it, and then their voice goes like this. I don't actually have helium. I'm just trying to falsetto, and it's difficult for me. But inhaling helium makes your voice go way higher because the density of helium is way lower, and density of air affects your voice. Likewise, if you inhale like krypton or xenon and then start talking, you sound demonic. You sound like this. I can't go much lower with my voice. But that's all it does. It doesn't affect you, like, chemically in any way. And it turns out that that non-reactivity has to do with the electronics of those atoms. If 8 valence electrons are on the outermost ring of electrons, not ring, I'm sorry, shell of electrons, then the atom or ion that is formed is relatively stable compared to how it was. That's not to say that it will always be completely unreactive, but it will be much less reactive than it would otherwise. So atoms on the periodic table have a tendency to try and get 8 valence electrons. If they have 8 valence electrons already, they are stable and do very little chemistry. If they don't have 8 valence electrons, the atom tries to attain 8. And this can happen either by adding electrons or removing electrons. We'll show how removing works in just a second. Adding should be pretty straightforward. And so this is called the octet rule. An atom will try to get 8 valence electrons so that it can resemble a noble gas and then thus be less reactive. Now, in doing so, atoms will turn into ions. They have to, right? So if I am an atom with 7 valence electrons, and I want to become an atom with 8 valence electrons, I inevitably have to do this, right? Because gaining an electron means that the number of protons and electrons is now different. And thus I will have an ion. So just be clear on the lingo here. That when we do this and attain an octet, if I am changing the number of electrons, I am also changing the charge of the atom. And so this is how we create ions. All right, so let's look at some examples of how this works. So here's an oxygen atom that I have drawn out. Oxygen has 6 valence electrons because it is in group 16, right? Okay, how do I get it to have an octet? Well, if I have 2 extra electrons lying about, I can just add them right in. So one would go here, and the other would go right there. And then I would get this as my result. Instead of oxygen, I would have O2 minus. The charge at the top is going to indicate how many more electrons I have if it's negative, or how many fewer I have if it's positive. So when I add electrons, the ion that's formed has a negative charge. And that's just because the number of electrons is greater than the number of protons, so there is an overall minus charge. Electrons are negative. All right, so if I have to add electrons in here, it's pretty straightforward how to do that to get to 8. But what if I have to remove electrons? How the heck do I get from sodium's 1 electron to 8? Now, you could add 7 electrons. But it turns out that there is an easier way to do this. And to do that, we're going to go back to the pictures that I showed you over here. Let me clear this off of the screen real fast. All right, so I'm looking at potassium here. And I have 1 electron on the outside. Now, let's suppose that I removed that electron. If I did that, this is what would happen. And I hope this works. I have to, I can't see my pen, but... So, I have removed the electron on the outside. I'm trying to white out this outer ring here, but it's hard when you can't see where your pen is. Oops. I got some of the inner ring. There we go. That's good enough, right? if there's no electron there, the entire ring doesn't exist anymore, right? The new valence shell would be the next ring down. So now, this is the valence shell. And how many electrons are in that? Well, there's 8. So our objective is, if our objective is to get to 8, we have 2 ways to do that. The first is we can fill in electrons and give it a minus charge, or we can remove electrons and give it a positive charge. Whichever way is easier to get to 8 is what atoms will do. And so that's what we're going to do. So we'll go back to this slide right here. There's my sodium with 1 valence electron. I'm just going to get rid of it so that it looks like it has 0 valence electrons. But in reality, what has happened is that the next layer down is the octet. And you can see that back here on this diagram. With sodium, it would just be layer 2 is now the octet as opposed to layer 3. Because sodium's in period 3, you remove the first electron on period 3, and now you have period 2. Okay? Now, if you remove electrons from a small atom, like say lithium. Lithium only has 3 electrons. There's no way it can get to the octet by removing an electron, right? But because helium is a noble gas, if you do this to lithium, so we'll just draw this right here. So here's lithium. If I just remove its electron, it now has 2 valence electrons, which looks like helium. And that's good enough. So for very tiny elements, the octet rule doesn't work because there just aren't enough electrons. But for all other elements past, like, say, carbon, so carbon and beyond, everything follows the octet rule. All right. So in summary, when you add valence electrons to something, if they have 8 valence electrons after you're done adding, the result is stable. Likewise, if I have 0 valence electrons, the next layer down is going to be the octet. And so we'll just treat it as such. Now, do you have to draw the dots for the octet if you have removed all the electrons? No. If you have 0 valence electrons after you've removed your electrons from your atom and formed a cation or positive ion, then the convention is not to draw those electrons. So we only draw electrons when you are adding to get to 8. All right, so now our goal becomes, what ions actually form? So to start with this, the first thing that I want you to do is I want you to draw these examples out. So start with the basic element. Let's do the first one together here, because we've already sort of done potassium. I'm going to start with potassium here. Potassium is in group 1 and has 1 valence electron. Now I'm going to do this to it. I'm going to make it positive, which means that I'm going to remove 1 electron. Now that I have done that, does it resemble a noble gas? Is there an octet? So for potassium, the answer is yes, there is an octet, because 0 counts as an octet. Now, if you do that for calcium with 4+, and you go to the periodic table and see that it has a certain number of valence electrons, and then you remove 4, do you land on an octet? If the answer is yes, then say yes. If the answer is no, say no. So I'm going to number these for you. 1, 2, 3, 4, 5. And so you just fill the chat with like 1, no, 2, yes, whatever, right? I'm going to give you 2 or 3 minutes to draw those on your paper, and then we'll go over the answers. So I'll see you in a bit. All right, one more minute. We'll go over the answers here. All right. Where did my pen go? There it is. Okay. So let's look at calcium here. So calcium... Oops. You know what? Let's just hit erase. Let's try that again. So calcium has 2 valence electrons. So we'll draw them. 1, 2. But I need to remove 4 electrons to get this as my result. So in order to do that, I would have to cross out these 2. And then I'd have to cross out 2 more. So whatever my octet was that was here, I guess, we'd have to get rid of 2 more of those too. So you could easily see that, this is not an octet. So calcium 4 plus is not an octet. How about Br minus? So bromine has 7 valence electrons. I'm going to add 1 so that I get Br minus. Well, if I had 7 and I add 1, I now have 8, which is an octet. All right, I've sort of run out of space here, so I'm going to go over to this screen. Those are still on the screen. Okay, cool. So let's look at now N2 minus. So nitrogen, that's not the pen tool. That's a box. There we go. Nitrogen has 5 valence electrons because it's in group 15. And to make it N2 minus, we would have to add 2 electrons. So here's the 5 that I started with. And then we'll add 2 more. Is it an octet? Nope, I'm missing this one, so not an octet. What about aluminum 3 plus? So here's aluminum. Aluminum is in group 13. It would have 3 valence electrons. To make it 3 plus, I need to remove 3 electrons. So here we go. We'll just get rid of 3 electrons. 1, 2, 3. Do I have an octet? Well, there's no valence electrons left. The next layer down becomes the octet. So this is an octet. And then finally, phosphorus with a 3 minus. So phosphorus has 5 valence electrons. If we add 3 electrons to make it phosphorus 3 minus, here's the 5 I started with. Plus 1, plus 2, plus 3 electrons. Hey, it's got an octet, so we have an octet there too. Alright, so hopefully this exercise has helped you draw Lewis symbols for more practice and then adjust the number of electrons and understand what that means in terms of the charge that you write. Because the next thing that we're going to do is we're going to compute charges without drawing the pictures, just so that you have more practice with like, oh, a negative number means more electrons, a positive number means fewer electrons. Because that's really the trick to knowing how to deal with charges, is getting into that mindset. All right, so this is where I formally introduce the concept of ions. An ion has different numbers of protons and electrons, and we've been working with these all throughout class today. We're going to be moving electrons to and from atoms and rearranging their number of electrons. But the number of protons will always remain the same in a given atom. Now, if you have more electrons and become a negatively charged ion, the term that is used is anion. An anion is a negatively charged ion. It has more electrons than protons. If you are positively charged because you have fewer electrons than protons, then the term that's used is a cation. Now, the way that I remember these two things is that if I write cation, the positive charge is already in the word cation, right? The other way you can do this, and this is where I wish I was in front of the class actually demonstrating this, because I would do the lucky cat thing, is the mnemonic cats have pos positive. And so you remember that. Whatever way helps you remember that cations are positive, anions must be the other one. All right. Now, as shown in this table here, if I count the number of protons in each of these sulfur ions or neutral sulfur atom on its own, they're always going to be 16. There's always 16 protons in sulfur. But you can see that the number of electrons in the table, as I move left to right, changes, right? The more electrons there are, the more negative the charge is. So when I have more electrons than protons, my charge becomes negative. When I have fewer electrons than protons, my charge becomes positive. All right, so what I want you to do... Oh, I thought we were going to the exercises here, but that's okay. So if I wanted to write a symbol for sodium with one fewer electron, I've taken an electron away from it. The way that I would do that, instead of drawing the Lewis picture and then crossing things out, is I would say, okay, here's the symbol. Loses one electron means one fewer electron than proton, so its overall charge would be this. So this should be relatively straightforward. How would I draw a nitrogen atom that gains 3 electrons? What ion would I write? So there's nitrogen, and if I'm going to give it 3 electrons, electrons are negative. There would be more negatives than positives in the atom. I would write that. All right. We're at our break, so what I'm going to do is I'm going to put this on the screen here, because I think that's the end of the section, yeah. So I'm going to let you try these problems over the break. We have 10 minutes. You could do these 4 symbols. You could type the answers in the chat if you want to during the break, but... Sorry, I was reading your comment. So, so for sodium, it wouldn't be -3. It'd be +1. The convention when we write the charges, I think you meant nitrogen though. When you write charges is you write the number first. Then you write the charge. Now if you write nitrogen -3, like this isn't NetHack, so it's not a cursed atom. Other scientists would recognize it with the charge first and then the number, but then they would laugh at you because, oh, you must be new. Because that's not what is done. So the number goes first and then the symbol. On Canvas, it's important that you do it in that order because it won't recognize it the other way and it'll mark you wrong. But yeah, it's atoms are not Dungeons and Dragons magical items, so like it's not that you have a +1 sodium atom, it's a sodium plus atom. If you only have one of something, then we don't indicate the number, so no number 1 is needed. Just like we don't write, like, in CO2, we don't write C1O2. All right, I'm going to put these description back up real quick. You can pause the video if you need these, but I'm going to go to the break timer right here. And we'll get some more music going from today. It's Donkey Kong Country 2. So we'll see you in just a little bit. If I can find the right song. There we go. Alright, we're back. So hopefully you've had time to draw, or not draw, I guess in this case, but write out the answers for these problems here. Because I'm going to do that right now. So you'll notice that now I'm starting to pick atoms in the center of the periodic table, whereas I wasn't before. Oops, chlorine's not in the middle. I thought that said something else. And there's sort of a reason for this. Any atom can gain or lose electrons, and we can write the result pretty trivially, right? So if I have copper and I take away 2 electrons, it'd look like this. And if I gave a sulfur atom 2 electrons, it'd look like that. And so on and so forth. And I can just do this all day. Platinum loses 4 electrons. There you go. Chlorine gains an electron. There you go. And hopefully you've noticed that I'll just relate if I'm losing an electron, that's positive, and if I'm gaining, that's negative. So you can write these symbols out very easily. No problem. I thought that there was like a table that we were going to fill in with these. I guess not. Okay. Just peeking ahead at my slides here. Alright, so now that we've put all of this information together, let's form ions that should occur using both of these rules that we just learned. So we talked about the octet rule and we talked about ions. So let's put that information together and figure out what ions will form for substances. For instance, sodium is always going to form sodium plus. And the reason for that is because of the octet rule. If I want to get an octet, I got to get rid of this 1 electron. Since I've removed 1 electron, this is the ion that forms. Likewise, if I did, say, oxygen, oxygen has 6 valence electrons. To get an octet, let me draw it 6 back here. I would need to fill in the other 2, which would be that, and then this is the ion that forms. So atoms will always try to satisfy the octet rule, and whatever ion they land on is going to be the ion that forms. So again, atoms will always try to satisfy the octet rule, and as a result of that, they will gain or lose electrons to get to their octet. And there's only one way to do that. Now, here I've written something about the closest noble gas. This isn't the best rule, so I would ignore this for now. This works great for elements before element 20, and then it starts to not work so well when you're trying to get the same number of electrons as a noble gas. But for things like neon and stuff like that, it works okay. There's just a lot of holes in that explanation. I know your textbook has that, but I would recommend right now stick to the octet rule, add electrons to get to 8, or remove electrons to get to 0. And that will predict what ion will form. So we've already done oxygen here, so I'll skip that example. But all right, I'm going to give you a bunch of elements here. And what I want you to do is I want you to tell me the ion that forms. So the way that you should start this, we'll do this example for barium. Start by drawing the Lewis symbol. And then say, okay, what do I have to do to get to an octet? You can either add electrons or you can remove them. In this case, removing 2 gives us the octet, and that's the ion. This would be the ion that forms barium plus with a 2+ charge. So do that process for aluminum, phosphorus, selenium, etc. If you already have an octet in the case of krypton, what do you think is going to happen? What ion would you form, if any? Something to consider. When you've finished these problems, we'll number them here. Write the ions in the chat. So you could write Ba2+ pretty easily. So I would write that like this. Ba2+. There you go. Something like that, for example. All right. I'll give you 2 or 3 minutes to try this, and then we'll go over the answers. So I'll see you in a bit. All right, one more minute. We'll go over the answers here. All right, let's go over the answers. So for this first one, aluminum here, if I draw aluminum with its 3 valence electrons, and I want to make an ion out of it that follows the octet rule, I would have to remove these 3 electrons to make Al3+. That would be the ion that forms. For phosphorus, I have 5 valence electrons. I would have to add in 3 more electrons. I'm going to draw those as circles here so you know which ones I've added in. And so this would, oops, I tapped the tablet there. Let me do that. And so that would look like this. So 1, 2, 3, 4, 5, 6, 7, 8 has an octet with a 3- charge. So I'm drawing the Lewis symbol. I drew all the electrons. But if you just did this, that's fine. So selenium is in group 16, has 6 valence electrons. I got to add 2 more to it. Like that. Krypton has 8 valence electrons because it's already in group 18. You don't have to do anything to it. So it just sort of exists on its own. So the ion that forms for krypton is no ion. It just stays krypton. Haha, surprise. And then astatine here. Group 17 has 7 valence electrons. We'll just add 1 electron here to get this. And then it would have an octet. There you go. So you now know how to draw the correct ion as a Lewis structure or just write out as a symbol. And so those are the ions that form for given elements. Now, you might notice that if I go to the periodic table, which has fallen asleep on my computer here, that the only elements that I've been picking for these examples have been in this box over here or this column over here. And I've been avoiding the ones in the middle here. Why is that? Turns out that the elements that follow the octet rule are only the ones in groups 1, 2, and 13 through 18. So that's why I've been specifically giving you these elements. 1, 2, and again 13 through 18. Those are the ones that follow the octet rule. These in the middle don't follow the octet rule completely. There are many exceptions. So while they can form ions, I have to tell you what those ions are. Oops. I hit a button to clear something off my screen and it tabbed me over. While elements in the middle can form ions, I have to tell you what those ions are. You cannot predict them based on the octet rule. There are other ways to do that, but they're beyond the scope of this class. So you will never have to draw a Lewis symbol for an element that is not in groups 1, 2. Let's write that down. So octet rule is groups 1, 2, and 13 through 18. So you're never going to have to do this process for any element that is not in those groups. Like, I'm not going to hand you iron and say, what ion does iron form? Because there's no way for you to tell. At least not at this point. I have to give you that information that iron becomes +2 or +3 or whatever. Okay? So just keep that in mind. There's the homework practice down below. Let me know if you have any questions. All right, let's continue. So now what we're going to do is we're going to talk about how we make compounds using the octet rule. Because if the goal is to make ions that attract to each other, I first have to do these steps. And then and only then can these combine to form a compound. So our mission in this lesson is to explore, how do I do this step? Because the ionic bond formation is pretty straightforward. Now, we've already shown how this happens in theory. If I have 1 valence electron, I'll just get rid of it. And if I have 7 valence electrons right here, I'll just add an electron in there. Well, what if I introduce these two things to each other? What happens instead? Well, I'm not going to get rid of an electron to get it out of the ether and then just absorb one from nowhere. I went through an electron on accident there. But that's okay, I'm going to erase those lines anyway. That's not what I meant to do. Anyway. Let me draw that in again real quick. So here's my electron I need. Here's the electron I want to get rid of. I'm not just going to toss this electron away and then add in an electron. Instead, what I'm going to do is not hit the button that I hit last time. What I'm going to do instead is this. Hey, I don't want this electron, but you need an electron. And guess what we call this? This is a chemical reaction. So when sodium and chlorine bump into each other, elemental sodium and elemental chlorine, they realize that they have something the other needs. Sodium has an electron. It doesn't want it. It wants to get to an octet. Chlorine needs an electron to achieve an octet. So they work together. And sodium will pass an electron over to chlorine. And when that happens, it looks like this. So let me prepare the video here. There we go. Let me see if that just captures it right there. That's pretty good, actually. All right. This is Lonnie. Lonnie teaches at UC Berkeley. I'm going to just zoom this in. I'm just also going to do this because he's creepy in this picture. So, I have this muted so that YouTube doesn't yell at me. But, let me turn off the captions because I'm going to just speak over this. All right. So here, what Lonnie is doing is he's putting chlorine gas into this container. And you can see, let me pause the video real quick. See that the yellow tinge? So like his white lab coat, you can see that it's a little bit yellow when looking through the cylinder. Chlorine gas is a pale yellow gas. And it is very, 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 very toxic. But you'll notice that Lonnie doesn't have any sort of face mask or shield or anything. It turns out that he is okay because this right here is a fume hood that is pulling air straight down. So any chlorine gas that might be seeping out of here poses him no risk because it's all being pulled into the fume hood. What's more important is that his hands don't contact it because it would react with his skin and cause corrosion in the form of burns. So that's the container with chlorine gas. So now we're going to get the sodium. So the sodium is stored under oil. It's not stored underwater because, as we saw earlier, the sodium would explode on contact with water. So we're storing in mineral oil. He's going to dump it in this container that has hexane to rinse off the mineral oil. Hexane burns away really quickly, which is where the sodium is going to go in just a second. So he's letting that soak. He's going to put his equipment on, because there is a risk of explosion when doing this. It's minimal, but it's not zero. So Lonnie's going to put the sodium metal into a ladle, and he's going to heat it up just so that it's hot enough to start the reaction. And so it doesn't take very long for this to happen. Sodium's melting point is not super high. So after a few seconds in this flame, you see this bright orange flame, which means that the sodium is now starting to ignite. And we're going to put it into the chlorine gas, and this happens. So all the exhaust that is being made by this is actually sodium chloride. It's salt, except not in the solid form. It's in the gas form. Gaseous table salt. You can see it getting sucked down the fume hood. Now, this reaction is extremely exothermic. It makes a lot of energy. So much so that the ladle that the sodium is being cupped in, when he pulls it out, I'm going to hit pause on this. You can see that the ladle is red hot. And that this stuff in here is extremely hot too. But what it will do over time is it will begin to cool down, and the ions that have been made will then collect together. And when they have done so, they will form this. And hopefully YouTube will move the... I guess it won't. What if I click on something else? No, okay. You can't really see it, but right here behind the timestamp, or the time bar where my cursor is pointing, is table salt. So if I hit play, you can see that. And in fact, it is actually table salt that he has produced. And just to demonstrate that it actually is edible, Lonnie's going to break like the #1 rule of lab, which is eating in the lab. So this is a hard-boiled egg, and you can actually just salt it with the table salt that you've created in this reaction, because it's literally sodium chloride. So, very good, Lonnie. You've earned your break. We'll see you next time I teach this class. All right. So, visually, that was the process by which an ionic compound formed. Lots and lots of energy was released. And the electrons move from the one atom to the other in doing so. Now, you need a little energy, just like how you have to strike a match with by dragging the match head over, like, the not corrugated, but the textured part of a matchbox to give it enough friction to start the reaction. We needed to heat the sodium up to give it enough energy to start the reaction. But once it did that, it stayed going on its own, passing electrons from sodiums to chlorines to form the ionic bond. And as those ions that are floating around in the gas phase slowly come together, they will make a salt crystal. All right. So here is how that was happening at the atomic level. Here are my two atoms. And I drew this earlier. To give everyone the octet rule, I would do this. Take that electron off of sodium to give it an octet. Add the electron to chlorine to also give it an octet. And so there's the ionic compound that I form, is NaCl, to balance out the charges. Now, at the top there, my reaction, I had to have 2 of each to balance out the equation. And the only reason for this is because chlorine comes in pairs. So I would need 2 sodiums to do that. We're going to talk about balancing equations in, like, Unit 8, maybe? Maybe in Unit 6. I forget. Later on in the quarter, though. Okay, so using our goal of getting complete and full octets, we're going to make ionic compounds following this sort of idea. Step 1, write out all your atoms. Step 2, move the electrons around so that everyone has an octet. Step 3, whatever you have is your ionic compound. All right, so let's do another example. Let's suppose that we had... I gotta look at my periodic table for this. Where is my periodic table? I have like a paper one, or it's laminated actually, that I have on my desk. So I'm gonna use calcium, and I'm gonna use fluorine. Calcium is in group 2, so it has 2 valence electrons. Fluorine is in group 17, and so it has 7 valence electrons. So I want to make an octet for everything. So the first step I would do, so I would move this electron over here. So now this fluorine has an octet because it has received an electron. Can't receive any more. Does my calcium have an octet? If it did, we'd be done, and the formula would be whatever's there. But you'll notice that there's this other electron and it's nowhere to go. I need to get rid of it too in order to have an octet. So what I need to do is I need to recruit another fluorine here. And I will pass this electron to it, so it has an octet, and now my calcium has an octet as well. I accidentally drew an extra line here on my fluorine, or my calcium. We'll do that. So now that I have formed this, what is the ionic compound that forms for this substance? I used a calcium and 2 fluorine, so this is the ionic compound that I would make, calcium fluoride, or CaF2. So if you are in a situation where you're trying to move electrons around, and it turns out this is most of the time, you end up with an atom that is not have an octet rule satisfied. Then you have to add in more of the other things so you can pass electrons back and forth. And you keep doing this until everything has an octet. You can't stop at the first octet. Everything must have an octet. Once you've done that, you just count how many you have, and that's your formula. All right. We've already talked about how you make your ions and how they attract through the ionic bond. So there you go. So what I want you to do is doing those sort of little football diagrams where you're like moving the dots around. I want you to tell me what the products are. So turn each of these into ions by fulfilling the octet rule, and then count up the total, and then write the result. What is the ionic compound that forms? K plus Br makes what after the ionic reaction? This is the cool part of chem. Yeah, we're actually at chemistry now. No more calculating how many miles an orc has to ride on his motorcycle to get to Seattle, right? Like, we're done with that shit. Now you get to make crazy things. So you can immediately go out and get calcium and oxygen and make calcium oxide or whatever. Let me number them. I'm going to give you a few minutes to draw the pictures here, and then we'll go over the answers. Once you have your ionic compounds, write the formulas in the chat as best you can. Obviously, I know you can't do subscripts, but you could just type out the letters. One more minute, we'll go over the answers. All right, so let's go. First, we got to go over here, because we're going to need a lot more space to do these problems. All right, so for the first one here, if I draw my potassium with 1 valence electron because it's in group 1, and my bromine with 7 valence electrons because it's in group 17, then to get an octet for both, I just pass 1 electron over like that. So this is good. It has an octet, and this is good. It has an octet. So the result that we would get would be then KBr. Now, if you wanted to look at the ions that were formed from this, you could say, well, I've made a K plus and a Br minus. We're going to look at that in the next section. Here, I'm just going to show you this graphically to move around valence electrons. All right, so the next one, calcium and oxygen. Calcium has 2 valence electrons. Oxygen has 6. And I can move 1 right there. I kind of missed that. Hold on, let me try that again. And I can move the other one right here. So now this is an octet. I've got rid of my 2 electrons. This is an octet. I filled in the 2 that I need. This is the compound that I'd make. Now, how do you know which element to goes first? The convention is that we put the positive thing first. So just as a FYI, we're going to put the metal before the non-metal. All right. Magnesium and chlorine. Magnesium has 2 valence electrons. Chlorine has 7. So I'm going to do this first of all. We'll move this electron right there next to it. So this one's good, but I need more. I need something else to give the other electron for magnesium to, because I don't have an octet over here. So I got to go recruit another chlorine. I put the dots on in the wrong way. I was trying to do it quickly. But there's the result. I get another chlorine. We're going to give it this electron. So now this has an octet, and my magnesium does too. So what's my formula? Well, I used 1 magnesium and 2 chlorine. All right, for my sodium, sodium looks like this. Nitrogen looks like this with 5. So I need to pass over this electron. Oops, not down there first. We'll just do this. So this one's good, but my nitrogen now needs more electrons. So I have to get more sodiums in here. In fact, I need 1, 2 more. So I'm just going to do that. So now my nitrogen has the octet. Each of these has its octet. And so I can write the formula. Oops, wrong color. Sorry. I use 3 sodiums and a nitrogen. So I get Na3N. Be careful, NaN3 is something totally different. It does exist, though. And then finally, for the last one, for aluminum and oxygen, this is just a mess of moving electrons around. So aluminum has 3, it's in group 13. Oxygen has 6, it's in group 16. I can move 2 over to this oxygen, and then it'll be okay, right? So now this has an octet. But I still have a dot for aluminum that I need to fill in. Or I need to get this electron off of aluminum. So I need another oxygen to do that. So when I move this over, now this aluminum is fine. But now I have a space for another electron that I have to accept from something. So I need to recruit another aluminum to pass its electron over. So now this is an octet. But now this aluminum I just got doesn't have an octet. When does this end? We just have to keep doing this and passing electrons around until everything has an octet. And yeah, it takes a while to get there, but eventually we do, and what we have is the formula. There were 2 aluminum and 3 oxygen. So that's the formula of aluminum oxide. So this is how you do these structures using valence electrons and pushing them around all over the place. All right, let me know if you have any questions. So we're going to do one more exercise today in the last 5 minutes or so. And that is to do what we just did in the previous slides with the pictures. Now we're going to try and do that without drawing a picture at all. The pictures help us understand what's going on, but we can do that without the pictures because we know, now that you've drawn the picture, you know that this is the ion that forms, right? You know that this is the ion that forms. So if we can do this without having to draw all of those sketches, we can save ourselves some time. And the rule for forming an ionic compound is that the total charge of all the ions summed together must be 0. Because if it wasn't 0 and I had, like, say, a negative charge here, I would attract something with a positive charge towards it. And then the formula would change. So if I have any charges left over, it will attract things that are charged, and I will change the formula. And that will continue to happen until all of the charges cancel out and are zero. Once it's neutral, the formula no longer adjusts. So let's do an example for potassium and sulfur. So I know that potassium looks like this. So what ion will potassium form? It would form this ion. And then I know that sulfur looks like this. What ion will it form? It will form this ion. So by knowing what the Lewis symbol looks like, I can then predict the ion that will form. And so here are my ions. Does the total charge equal 0? So I've got positive 1 and negative 2. Those do not equal 0. I have too many negatives. So I'm just going to keep adding in these until they balance out. And so now I can say, well, I have two Ks and an S, K2S. So this is really just an alternate way to do what we did in the previous examples. So if you prefer the picture way and want to push electrons around, for most substances that will work, but for anything that involves a transition metal, it won't, because you can't draw a Lewis symbol for it. The reason that this method is going to be useful is because now I can give you any ion with a charge on it, and you can find the ionic compound, because all you have to do is balance out the charges. Okay? So that's your task now. All right. So let's have you do this example, selenium and barium. Tell me what the ionic compound is in the chat. I'll give you like 1 or 2 minutes because we're going to run out of time. And then I'll tell you the answer. And we'll go over the remainder of these tomorrow. I just realized I didn't do the lab stuff. I forgot to do that. But we'll do the lab tomorrow because I am going to use tomorrow as a lecture day. In fact, I'll set my alarm right now so that it goes off and I'll be like, oh yeah, I have to teach a class. Otherwise, I might go to the grocery store, and that's not something that I want to do. Be at the store and be like, oh, I have a class right now. That's not great. All right. So we have an answer. That is the answer. But remember that we want to put the metal first, so you just flip them around. But, oops. So I've got barium. Barium looks like this. So the ion it forms would be barium plus 2. Or barium 2 plus. Selenium looks like this. So the ion it would form would be this. These are the ions that I formed. Do they cancel out? They do. So the formula I have is just this. Barium selenide. All right. And then we did aluminum and oxygen earlier. I'll just do this example real quick because we only have 1 minute left. So here's my aluminum. This is the ion it forms. Here's my oxygen. Here's the ion it forms. And so you should know why this is because here are my... I'll draw the Lewis symbols in really quickly. Because that's what we've been talking about all day today. Do the charges balance out? Nope, I need more negatives. Oops, now I need more positives. Oops, I need more negatives again. Now they balance out. 6 plus and 6 minus, Al2O3. A lot faster than drawing the pictures, right? The pictures are helpful, though, so that we can understand conceptually what's going on. All right. I'm going to put the examples up on the screen here real quick so that I have the homework practice. So go ahead and do these. We'll start here tomorrow. Just as a refresher. And then that's the homework practice that I recommend for these exercises, for the stuff that we covered. So we have done, let's see, we're most of the way through. Yeah, so... Oh, we just have naming. Okay, so yeah, what we're going to do tomorrow is I'm going to do the naming stuff, and then we'll do a little bit of Unit 5 after we do the lab. In fact, I'm going to start with the lab so I don't forget. But then we'll be back on task for lectures and stuff. So I do have to use tomorrow as a lecture, which means we have to come in on a Wednesday. Well, I mean, you guys don't have to come in on a Wednesday. I do. I have to record it. You can watch it whenever you want to, if that is what works for you. So I do want to thank everyone for coming out to the lecture. After tomorrow, there will be a quiz that goes up for Unit 4. It'll be due next week. So you'll have that in addition to the quiz that's for Unit 3. But for this week, quiz number 2 is due tomorrow. It will close on Thursday, so make sure you get that done. And again, we'll talk about the laboratory stuff tomorrow, so we'll do that then. That's all I really have. So have a wonderful rest of your evening. We'll see you tomorrow. And let me know if you have any questions in the Discord. Take care.